Welcome, everyone. We're excited to have you join us for today's session on creating sustainable labs and critical environments. Whether you're new to the concept or are already implementing smart strategies, this webinar will offer insights, tools, and real-world examples to help you optimize lab environments. My name is Mallory Millen, and I will be your host today. Before we begin, here are a few quick reminders to help you get the most out of today's session. All participants are currently muted to minimize background noise and ensure a smooth experience for everyone. Please use the Q&A function to submit your questions at any time. We'll address them throughout the presentation and highlight a few live during our closing Q&A session. If we don't get to your question, we will follow up with you afterward. We'll also be launching a few poll questions today to better understand our audience. Your responses are greatly appreciated. Finally, at the end of the webinar, we'll also ask you to complete a brief survey. Your feedback helps us improve future sessions. And today's webinar is being recorded, and you'll receive a link to the recording within 24 hours via email. Next, I'd like to introduce you to our expert presenters who are going to tag team the presentation today. Jim Coogan is a principal engineer here at Siemens with over 4 decades of experience designing advanced control systems for HVAC and laboratory environments. He holds more than 20 patents and contributes to ASHRAE standards, including TC 1.4 and Guideline 36, as well as the Z95 lab ventilation standard. His published work spans room pressurization, lab airflow strategies, and building automation protocols. Sarah Grady is a licensed professional engineer and certified energy manager at Siemens, specializing in smart lab and building systems. As a project developer, she leads the design and deployment of energy-efficient, resilient infrastructure. Her expertise spans sustainability, critical environments, and strategic project execution. But first, before we get to the agenda, let's take a quick poll. This will help us tailor the conversation and make the session even more relevant for you. So if you could, let us know, what is your role? And then once you make your selection, just please hit the X or hit the X to exit out of the pop-up to continue. And then let's see who we've got here. It looks like we have other things are changing here. We've got a handful of facility managers, HVAC contractors, and a lot of other, so that's great. And we have a full agenda today. So we're going to start with the basics. What exactly is a smart lab? We'll define the term and explore how smart technologies and data-driven strategies are transforming lab operations. Then we'll discuss why labs are among the most energy-intensive spaces within any facility. Next, we'll review how smart labs reduce airflow safely with proper ventilation, and we'll walk through how LVMPs, or laboratory ventilation management plans, assess risk and guide ventilation strategies tailored to specific lab activities. Then, how to monitor for energy analysis and ventilation performance. And we'll bring it all together with real-world examples, with case studies to show smart labs in action, and wrap it up with answering your questions submitted throughout the webinar. And with that, I am pleased to hand things over to Jim and Sarah to get us started. Jim and Sarah, take it away.
Hello, everybody. I'm Sarah Grady, and basically what I want to talk about was what is a smart lab, right? So a smart lab is one that is using a comprehensive digital optimization strategy. So this basically means we're installing controls and gathering data to create a proactive lab environment that's going to adjust with your use in order to save energy and also enhance safety and comfort. So to do this, we're basically going to use data analytics, predictive maintenance, and digital services, all with the end goal of making a more sustainable and a more energy efficient lab. Next slide. So when we ask why laboratories, the answer becomes evident as soon as we look at the energy intensity use compared to other types of buildings. So you see on the left here, a typical office building has around 100 BTUs per square foot annually for its energy intensity. A hospital or healthcare might be as high as 200. Laboratories, however, tend to range between 350 to 850. And this is due to the once in, once out nature of the ventilation. So 100% outside air is heated or cooled, dehumidified, only to be immediately exhausted once it leaves the laboratory. So if you look at the pie chart over on the left, as an example laboratory, you can see that 44% of the energy is associated with ventilation, an additional 22% is associated with cooling. So since these numbers are all driven based off of the high air change rates, if an older laboratory has around 12 air change rates and we're able to reduce it down to an average of 6 air change rates, we're saving approximately 50% of the energy associated with ventilation and cooling, which equates to 33% of the entire building's energy use. Next slide.
So what is sustainability? This is another take on the same question. And in my mind, the best definition is that we're preserving the environment over the long term. It's not something we do today or tomorrow. It's something that's the evidence and the effects and the evidence are really in the long term operation. So and the main idea is preserving the environment in such a way that future generations can do the same kind of things we're doing, which means we need to adjust what we're doing to enable that future use. So there's a lot of environmental issues involved here. Two of them really work into our wheelhouse here. One of them is the energy use, and the other is the indoor environment. And indoor environment, how's that a sustainability issue? I'm gonna assert that if you're today your environment's not healthy for the people working for you, that's not a sustainable situation. And so the indoor environment and the energy use together are the top of the many sustainability issues. These are the top ones that we can adjust or affect when we're talking about laboratory and laboratory ventilation. So how do we address these? Well, design and construction are really important steps. That's where we start. We start with, the building gets designed or redesigned, and we build it or renovate it, and that's when we do our hardcore construction work. But in the long run, the energy use and the environmental conditions, they happen in the operating phase of the building. Like I said, design and construction are important steps, but it's a long-term operation. It's important, and that's why we need to continue to look at how the thing performs day after day, year after year. It's not enough to have built or designed a good system. You have to keep it running right. You have to keep it running in that intended operation.
So when we talk about what exactly the benefits of a smart lab are, then it's all about using the technology and data to take these high energy intensity laboratories, use the data and smart controls to reduce the energy consumption. So this can include incorporating occupancy schedules or sensing, as well as hazard sensing to enhance the safety for the laboratory users. And it also reduces the energy use. So often these measures can be paid back between 4 to 8 years. And they also provide a visible commitment to corporate or client sustainability goals.
So if you want to reduce energy use, first you got to understand where you're using energy. And this simple diagram of a laboratory ventilation system showing an air handler at the top, bringing in outside air with a fan, goes through some coils that heat and cool it, and that air gets distributed out to many different rooms. At the room level, there's another air terminal typically to regulate the airflow, and maybe additionally heat or cool the air again here. Okay. And then it goes through the room and maybe out through fume hoods or other exhaust devices, and up through exhaust fans to exit the building. I'm showing individual exhaust fans here because this is an old picture, but the idea is still the same. The circled elements here are where we're consuming the energy. Electricity to drive the fans, hot or chilled water that was generated by other kinds of fuels, electricity or gas. And this is where we consume the energy. Knowing that, we can think about how it gets used up. The fan energy is really sensitive to the amount of airflow, okay? It's it's not just linearly increasing with the airflow, but it increases it's somewhere between a second and third power of the airflow. So fan energy, fan power is very strongly affected by the quantity of airflow. The heating and cooling processes are also strongly affected, at least linearly. If you double the airflow, you double the heating load, you double the cooling load, all the conditioning. And so all of these energy uses are strongly influenced by many factors, but strongly influenced by the quantity of the airflow. So when you're saying, what are my energy conservation measures? What can I do to reduce energy? The first thing to do is use less air. And that means use less air in a way that you have to pay attention to what you are using it for and how do you achieve that effect at a lower rate. Okay, so you don't just indiscriminately use less air, but using less air is the biggest effect on energy use. Also important, but less important, is to improve the heating and cooling processes. If you make that heating and cooling process more efficient, if you design something that uses, it reduces, say, simultaneous heating and cooling, or makes better effect of energy recovery, then you're going to improve that process, and that's going to cut the heating or cooling load. That's important. It's less significant than reducing the airflow. Okay. And the third lever to pull here is going to be moving the air more efficiently. And that means things like better exhaust fan strategies, or low pressure air terminals, or duct pressure reset functions. These are the things we can do to move the air more efficiently. That's important too. And I'm not saying you don't do these things. They're really important conservation measures here, but it's the third tier. Number one is use less air. Number two is heat or cool more efficiently. Number three is move the air more efficiently. And when we go into the large menu, Sarah's going to talk about a lot of energy conservation measures. This is a good way to keep them in mind and rank them, and say, where's our best opportunities? Where's our least or less valuable opportunities? Next.
So once we understand what's really driving the energy use, we can start to look at what we can do to reduce it. Much of the energy use is driven through ventilation, like we talked about earlier. And most facility improvements then focus on how we can reduce the required airflow load, just like Jim was talking about. So what I've got here is just a list of different types of measures specifically that we might look at for laboratories. So first, we're going to look at fume hood flow reduction. Can we convert it from constant volume? Can we do better sash management? Are there possibilities for low flow or even ductless hoods? And when the labs are vacant, can we do something like hood hibernation? We're also going to look at room airflow reduction. So a lot of this we're going to touch on a little bit more in detail later, but can we match our rate to our risk? Can we lower our air change rates when the room is unoccupied? And can we look into some sort of demand control ventilation? Finally, we're going to look at cooling load efficiency. Can we look at set points? Can we decouple our ventilation from our cooling for high cooling loads? And then fan optimization is really that last tier, but that's things such as static pressure optimization, exhaust fan staging, and then fan stack reset, things along those lines. Next. So when we're reducing our ventilation, it's really important to know and understand why the different spaces have the ventilation rate that they have. So laboratories can pretty much be split into three main categories for what's driving the airflow. We have exhaust-driven labs, which have a very high equipment load. Typically, these are fume hoods, and they often operate well above what the base specified air change rate required is. We have base ventilation drivers, which are already operating around the air change rates that have been specified. So any improvement measures there need to focus on how we can safely lower those air change rates. And then finally, we have thermal drivers. So these are ones that have a very high cooling load, either due to large windows or maybe a large concentration of equipment like refrigerators or freezers that are adding to the heat load. So understanding what's really driving the ventilation is key to understanding how we can reduce it. The thermal drivers aren't really going to be reduced unless the cooling load can be dispersed. And this is either going to be through relocation, spreading out equipment, or possibly decoupling it, maybe adding a split system or an additional means of cooling. For exhaust-driven systems, we're going to look at how we can lower the equipment exhaust load. And this might be reducing fume hood minimums, decommissioning or possibly hibernating fume hoods when possible. And then for the base ventilation, we need to ensure that the specified base ventilation is well matched to the existing risk. Additionally, occupancy should be taken into account. The air change rate is really designed to protect the occupants that are in the laboratory. So when no one is present, we can reduce it further. And the last thing that we really want to look at is demand control ventilation for laboratories. Next. So with demand control ventilation, what we're really doing is using smart sensors, which are put in place, installed into each of the laboratories to measure both the supply and general exhaust and determine the presence of hazards. This allows for a continuous feedback to the air quality of the rooms, and it allows for air change rates to be safely reduced further. And then if hazards are detected, this is often referred to as an event, we ramp up the air change much higher, right? So what this basically means, and it's got a little bit of a calculation here, assuming you're starting at like 12 air changes per hour. And if you can average down to like 2.5 air changes, and essentially the way you do that is by going down to something around 2 when it's unoccupied, you're usually a little bit higher when it's occupied, and then doing that continual measurement, you're talking about upwards of an 80% reduction on those, on the energy that is attributed to the laboratories. Next.
All right, so I'm going to start into a subject here about the Laboratory Ventilation Management Plan. And that's a long name for a big idea. This is one of the main ideas promoted in the ANSI Z95 Laboratory Ventilation Standard. It's a document for an organization, a scientific organization, to say, to bring together the topics of ventilation for safety and exposure control with the engineering equipment and operation aspects of the ventilation equipment, and a comprehensive, wide-ranging plan. And I think I'm going to it brings together safety issues. It brings together laboratory use issues and engineering and operation issues all in one place. Let's click ahead here. And it's time for the question. My question is, who's ever heard of a laboratory ventilation management plan? And here's your possible answers there. So we get some results coming in. Mallory, do we see some answers? Maybe not. Well,
Yep.
Without those answers, we're going to go ahead to what is a laboratory ventilation management plan. That complicated picture on the right is a diagram from the ANSI Z95 Laboratory Ventilation Standard. It is a complicated diagram, and my main point is don't let it scare you away. The Z95 standard is sort of the main proponent of this idea of a ventilation management plan, and they spell out that standard spells out in a great deal of detail, broad and deep guidance on what goes into a laboratory ventilation management plan. They spell out scope and what are the essential components, what are the pieces of the diagram or pieces of the document. They talk about stakeholders, an exhaustive list of stakeholders, contributors. It could be people who put information in, people who pull information out, how and when they use it. And what are the processes? And I mean, first of all, the people processes that support the safe ventilation. So how do we find out what we need and what we have, and how do we coordinate design with use, et cetera? There's this broad and deep scope of the document. I'm going to say again, it is comprehensive. And what I want to stress here is you shouldn't let that scare you away. If you see 20 topics and 4 of them really resonate with you, work on those 4, okay? And if there's other stuff you say, that's good to think about but doesn't apply to me, you don't feel constrained to check every box. It's comprehensive, and it starts with the purpose of the facility. I said this spans technical and operational issues. It starts with the purpose of the facility. Why do we have this laboratory? What are people doing here? How do we need the facility to support that work? That's the first thing you have to do. The facility has to support the work. Okay. And then we move into what are the hazards and the work hazards regarding the materials and how they're used in the laboratory, the work practices. And so that comes into this too. We can't say what kind of ventilation we need until we know what are we ventilating and how are they using it, what's causing that stuff to come up into the air, and how do we need to remove it. And then it extends through, okay, we move into that, and how do we design the ventilation system for the purpose we have, okay? How do we design it? How do we build it? How do we commission it? And heavy emphasis through in the Z95 standard and other places on commissioning. I like to say, if you need it to work, you have to make sure it works. And that's what commissioning is all about. This ventilation system, we need it to work. And that means we have to go out and meticulously determine that it is working as built and is in operation as well. So the Z95 standard calls out test to use it at the commissioning and acceptance testing, but also routine monitoring and retesting to go on to continue to maintain the intended performance. The ventilation and all that should be spelled out in the ventilation management plan. Again, it started with what's the facility for, work through how the user's going to use it, going to work there, and into then what do we need to build and what do we need to and what does it need to accomplish in physical terms. And then we come to training, and that should be there's more than one place that training comes up in an effective LVMP. Training for the people who operate the system, training for the people who work in the laboratory, training for the people who come and monitor performance, and even to come back and continue to monitor the use. Okay, the safety people like to talk about the topic management of change. We started with what are they going to do in this laboratory? Well, that might have changed before they even finished building it, okay? And an effective ventilation management plan will talk about how do you manage the change to say we're going to come back, we're going to come back and find out that one, they're using it like we thought they were, they're doing the work we thought they were going to do. Two, they're doing it according to the training that we provided. And so you go through this stuff and continue to monitor. It's not enough that it worked the day you set it up. You need to come back and make sure it continues to work. And that means that the equipment still works as intended and that the people are using it as we thought they were going to. If that's changed, then maybe some other stuff has to change with it. Consequently, building by building or facility by facility or enterprise by enterprise, there's going to be parts of this thing that are really relevant and parts of it they just kind of have to take a glance at and say, no, we don't really need to think about that. And I think that's the key to making this whole laboratory ventilation management plan work for you. The key is to use the parts that help you. That big diagram, it's nicknamed by its author the menorah diagram. That picture shows lots and lots of pieces and lots of uses. You should take that in, think it over, and say, okay, these are the parts that I need to pay attention to. Probably most facilities are already doing parts of this anyway. They might not have named it laboratory ventilation management plan, but certainly parts of this planning and an assessment, et cetera, certainly there's parts of it that they did. And they should look at this thing and say, is there a couple more pieces we ought to do, and pull that together, concentrating on doing the work that's going to help them. So, long talk about a complicated idea, but what I want to stress is don't let the complexity scare you off. Use the parts that help you. Next. So this just comes back to the idea that we talked about maybe a little sooner. Biological laboratories have one set of hazards. Chemical laboratories have another set of hazards. If you don't know what's going to happen in the laboratory, you have to think about it in a different way. And so, like we said, with the LVMP starts with how are they going to use the lab. That is where that's a really important topic, and you need to get your hands on it, or get a handle on it at the start, and continue to maintain that up-to-date knowledge of what's going on in the laboratory. What are the hazards? What are we trying to protect people from? And are they working in a way that makes that makes that effective. How do safety professionals do this? If we collectively took the challenge, hey, let's see if we can reduce ventilation. I said that was the biggest thing we can do to save energy is to reduce airflow. If we but we have to do it safely. If we collectively accept this challenge, we want to reduce the airflow rates. What's the safety professional? Where does he start on this? And they come in and evaluate the hazards, and they do that. I'm going to stress again. You do that ahead of time before when you're planning the facility. You continue to do it as it's used. Evaluate the hazards, and use that to think about: are we running these things at a higher air change rate than we need? Are we running more air than we need? When you ask that question, you can't help get into, well, how well is that air? Not how much are we ventilating, but how well are we ventilating? How do I know if 12 air changes is too much or too little until I see how well is it removing the contaminants from the building? And that's what we call ventilation effectiveness. The number isn't as important as the effect. And we want to see that regardless of what the number is, that we're doing the right job of removing the hazards. And if we're not, can we improve the way we ventilate instead of adding more or keeping it high? Can we improve the way we put the air in, the way we pull the air out, so that we do a better job of protecting the people and preventing exposures. There's a industrial hygiene concept called control banding that's used to address the fact that there are thousands and thousands and uncountable numbers of hazards, and we don't have a study on every one to say what's the exposure limits and what's the volatility, et cetera. We don't have all that, and so control banding enables us to put things in sort of broad categories and use those rather than trying to get specific information and specific data on every kind of hazard, every expressed hazard. Sarah mentioned that one of the things we're going to talk about doing is reducing the ventilation rates when the lab's not in use, and that requires careful assessment of the way the lab is used. There are rooms that are never unoccupied. There's always somebody doing something, or there's likely to be somebody there. And there's some where an unoccupied setback is really just not even practical to think about. But other places that are really run on schedules, people who have diagnostic test labs where they, the technicians come in and they punch in at 8 and they go home at 4 or whatever, and it's really well known when they're there and when they're not. What we do with that information is then consider, okay, well, if the people are gone, is the hazard continuing? And that's actually an important question. It's not, we don't want to talk about the people are gone and therefore we don't need ventilation. We want to say the people are gone, therefore the hazard is diminished. They're not doing that work that's generating the contaminants, and therefore the ventilation need is reduced. That's how we want to think about it. Well, if that's what we're thinking about, we have to not only say, are they here or are they not, but we have to ask, oh, is the hazard diminished? Do they have a pot of something that's still boiling on a bench, or have they put their chemicals away and stored them and closed their hoods? And so you have to talk about how is the lab used, and it's a step beyond did the people come or did the people go. It's what did they do before they left to reduce the contamination that happens while the room is empty. So there's a lot of things to think about, and some of it comes from the safety professionals, some of it comes from the lab managers, some of it comes from the ventilation designers. You need to put all that stuff together if you want to reduce ventilation consistent with a well-organized LVMP. And then I think Sarah picks it up to talk about how do we visualize this stuff and monitor it after occupancy and in operation. Sarah, your microphone's off. Oops.
Thank you for that.
Somebody had to do that once.
One of the things we really look at when we are talking about smart labs is how we can pull in digital monitoring, how we can pull in visualization, how we can really use data to our advantage. I guess if you go to the next slide, we've got some examples of the LVMP monitoring. Did you want to cover this one, Jim?
Sorry, I think we kind of lost the thread here a little bit. I mean, I have to admit. Why we're coming back to LVMP for the purpose of talking about how it leads into the long-term monitoring. And I said, you know, sustainability is not only about how you build it, is how does it really run? And safety is not about how did you build it, but how does it really run? And the LVMP is supposed to really make sure that we keep thinking through how does it really run. And so the LVMP is going to lead us to long-term monitoring. We don't only want to know that it worked the day we built it. We want to know that it still works later. And the Z95 standard is pretty explicit on a lot of really concrete advice on how to continue to monitor operation. The safety people are really into the plan, do, check, act. That's one of their big mantras is you not only make a plan, you execute it, and then you look and see if it's having the intended effect, and if it's not, you come back and adjust. Okay, and so if you're an engineer interested in quality assurance and long-term effectiveness, you're gonna you'll have an ally in the safety community if you put it in terms of the plan, do, check, act. And the Z95 standard supports that stuff with explicit suggestions on what would be useful to monitor. So as I said, there's a section on testing, and there's two sections on testing, or they'd split in two pieces. One is for the acceptance test when you finished making the facility available through in a construction project, and the second is routine tests to continue to monitor to improve or monitor performance. The standard doesn't tell you exactly how you should monitor the thing, but it tells you things you need to consider. And it says the owner shall consider automatic monitoring, building data analytics, physical testing, preventative maintenance, repair maintenance, to manage and maintain performance. So they talk about a lot of tools and say you need to think about the whole thing. They don't tell you exactly you have to do this, exactly you have to do that. But they do say consider the full set of tools when you make your plan and start to execute and monitor the system over the long term. And so automatic monitoring and building data analytics are pretty much are new kinds of tools here in the box. New kinds of tools, and you need to take advantage of the opportunity. Consider, how do I fit this together? It's really, I think, most useful to think about how do you put together those automatic computer-oriented tools along. How do you support those or complement those with on-site physical tests and preventative maintenance, et cetera. And thinking about that whole set of tools is a great way to find an operation that's going to work best for your situation and your organization. The standard further identifies a set of, if you want to do some long-term automatic monitoring, a set of variables that are worth looking into. I'm not going to read this list to you, but first of all, it starts with alarm states for all the exposure control devices. You should have alarms on your exposure control devices to say they're working properly or they're not. And you should be collecting that information so that not only does the lab user who needs it get the information, but it goes up to the facilities people and the safety people who repair or who manage these things. Fume hood face stash opening is a good thing to look at because it tells you stuff about how people are using the spaces, actions they're taking or not taking that affect safety and affect energy use. We can go on. Like I said, we're not going to read the whole list, but the standard gives you a good list of things that are worth considering as quantities to monitor.
So as we look at the digitalization, we really can look at how it can impact all areas of your facility, right? So one of the things that we like to do is have that digital monitoring that kind of ties in everything that we've talked about with the LVMP, everything that we're going to want to have eyes on. So the digital services can be used alone, they can be used in combination, and they're really designed to optimize whatever is most important for your facility and what you would like to see. So we created analytics for labs. It's primarily created because of the lack of visibility in lab performance. This causes a big problem. By performance, obviously, we're talking about operational and safety conditions, meeting regulations, managing compliance, and then also energy efficiency and sustainability. So analytics and fault detection diagnostics can provide the information that's going to show you exactly what is driving your operating and your utility costs up. It also provides clear, actionable tasks that'll help solve those problems. You're going to be monitoring and recording events and highlighting operational issues. And these might be things such as sashes being left open while the lab is unoccupied, or laboratories which are being operated in an unsafe manner. So on the next slide, I've got an example. This is our critical space monitoring report. This is just one of the examples that we have put together. And what this can do is you can track your pressurizations, your temperatures, your humidity, your occupancy, other parameters such as fume hood sash height, fume hood face velocity. And all this can be done kind of on a dashboard sense. And what this does is it allows customers at the user level or the facility level to interact with the data for smarter operational decisions. You don't have to learn a complicated building automation system, learn how to program anything, navigate sometimes multiple building automation systems in a single facility. It's just a single dashboard that can be used, and data can be brought in from a few different resources in order to build this dashboard, which can then just be pulled up on a phone, on an iPad, and you can basically get a very quick idea of, where's my pressurization off? Have I been keeping my temperature stable the way that I need to? And you can click into a single lab and see exactly how it has been operating for the past week, for the past day, and are you actually operating the way that you want to? So this is a really great way to visualize all the things that we discussed earlier in the LVMP, where not only have we written out how we want each lab to operate in our management plan, but now you have a way to visualize that it's actually doing what you designed it to do or what you told it to do, and easily be alerted when it is not operating the way that it's supposed to, in a way that is accessible to everybody in the laboratory and not necessarily having to have access to control parameters or logging onto the building automation system. So what I've put together next are a couple different examples where we have done facility improvements. Go to the next slide. I've got two different examples here, and these are retrofit laboratories. Just to give an idea, first one, we got a university building. This was one where we did constant volume to variable volume conversion. We did an air change rate reduction room by room, working with the university to determine what the safety risks are and what they could safely reduce to. We also did occupancy reductions. And this primarily comes into play with secondary ed because when you talk about occupancy reductions, it may seem like, okay, 40 hours a week you're occupied. Oftentimes the laboratories in universities, particularly the teaching laboratories, might be unoccupied as much as 80% of the time. And this is because you have summer breaks, you have winter breaks, you have teaching schedules, so you might only have people in there a couple hours during the day. So with this particular building, we've had the full measurement and verification afterwards. Our measured results, you have, I won't read out like the KWH and the therm saved, but essentially the end utility savings was over $100,000 in annual utility savings. And again, this is ongoing every single year, right? So our second example, it was a government environmental lab. This one was already a variable volume, but what we did was a controls upgrade. And again, going through that risk management, going through and looking at where can we reduce it? Can we add occupancy reductions, et cetera? And again, it saved a little bit less energy, but they had higher utility bills. or utility rates, and they ended up saving $64,000 annual savings. So essentially what we're going to want to do is anytime that we're doing these reductions, anytime that we're looking at these laboratories, it's going to be kind of a custom idea if we're trying to make an existing laboratory more sustainable. What are we starting with? What can we go down to? How are we working with the customer? Is it possible to reduce the airflow? Have they looked into what's being done in all the laboratories and everything like that? However, almost every single laboratory is going to have a substantial reduction, provided that they're starting with a higher air change rate. Once we actually get our smart controls in, once we're actually measuring and verifying the safety and making sure that people are operating the labs in a safe manner. Next. So finally, we've got a couple of resources at your disposal so that you can discover a little bit more about the critical environment offerings. So if you want to take a moment, you can use your mobile device. You can scan our QR codes, download whatever assets you might need. If you miss any of these or you have any trouble, of course, you can reach out to us. We'll gladly send them to you directly. The Smart Labs webpage is a great place to start if you've been interested in what we shared so far, if you want to dive a little bit deeper into smart or sustainable labs. The partner and locator tool is going to help to locate a Siemens sales office or representative nearest to you. Also, there's going to be a poll question next. You can answer yes if you want someone to reach out to you for further assistance. So I'm going to pass it off to Jim for our final poll question.
And the final poll question is, can we have a Siemens sales representative contact you to look at your possibilities for improving sustainability in your laboratories? And you can click yes or no, and we'll follow up accordingly. And that's it for our planned remarks. And I think we've got some questions that have come in. Mallory, are you handling that?
First, we wanted to just plug the I2SL conference. Both Jim and Sarah will be at the I2SL conference in Dallas, Texas next week. If you're there, please feel free to stop by their presentations. Sarah will be presenting on Monday, October 20th, and then Jim is presenting with another one of our colleagues on Wednesday, October 22nd. This is the contact information for both Jim and Sarah. Feel free to reach out to them via email at any time. And then, yeah, we did want to leave some time for questions here at the end. So I just wanted to thank everyone for participating and for sending in the questions that have come through. I'm just going to go ahead and get started, and then Jim and Sarah, you can feel free to answer whichever question you'd like. So the first question here that I wanted to ask is, are there mechanical limitations that affect whether or not these energy conservation measures can be adopted or implemented? Okay. Yes, there definitely are some mechanical limitations that are going to affect how we implement them. A lot of times it's going to affect our overall scope. So the main one is, if you have an existing building, is it already variable volume? Because a lot of what we're talking about is reducing our air change rates and being able to match the rate to the risk. And this is going to require a variable volume system. Luckily, we have lots of ways that we can upgrade systems if you're trying to do a variable volume and you have an existing constant volume. So it doesn't necessarily always require a rip and replace. There are retrofit kits available for Venturis so that they can be upgraded and converted to variable volume. We have for blade dampers, you're talking about possibly changing your actuators and upgrading your
changing your actuators and upgrading your controls for that. That's going to be the main thing. Exhaust systems, you're going to, if it's a plenumized exhaust system or not a plenumized exhaust system, that's going to make a big difference on how we treat the variability of the exhaust and fume hoods as well. If you have a bypass fume hood, there is a way that you can convert that to make it a variable volume fume hood, but it does require additional sensors and stuff. So yes, there are mechanical limitations, but they are all able to be overcome without having to tear down the building and create a whole new mechanical system.
I think
Great, thank you.
I think I'll just throw in one more point. A big part of whether it's what it takes to make a particular renovation feasible is what is the airflow ranges of the equipment that's installed, and that means the mechanical equipment. What are the min and max ranges that it can work reliably at, and the control equipment, especially the sensors. And what's the working range of those? And so Sarah mentioned you may need to replace some components to get to certain levels. You could look at, we want to take these airflows from here to there. Which are there? If there's particular components that can't get you there, what's involved in replacing that? It's mostly about the airflow ranges, and you have to look at the details of the components to find out what your options are. Sometimes you can just put in new numbers. Sometimes you need some new parts.
And sometimes you have to just adjust your calculations. I've had some jobs where a couple fume hoods might have been removed and they had a 14-inch VAV box supply, and the choice was essentially you can't go down as low as you wanted. So maybe you have a higher air change rate for that room, or you have to look at actually replacing the mechanical equipment in that room.
All right.
Next.
We got some more questions here. So I have an obsolete system. What are ways I can go about improving my energy efficiency on an older obsolete mechanical system? Are there measures not applicable to an old automation system?
Yes. Yes, and especially it depends on how it's obsolete, what's obsolete about it. One of the most likely things is if you want to move into remote digital service applications, remote monitoring and fault detection, etc. There's a good chance that and it's an old building, there's a good chance that the electronics, meaning the controllers themselves and the networks, are not up to the task. There's a good chance of that. And if you want to get to where you're going to be doing remote analysis on building data, good chance you need some new electronics if the stuff's really old. And you need to go to the modern networks. You need to go to up-to-date networks. You're probably not using a 2G phone anymore, and you need today's networks if you want to get to today's data-oriented services. That's one aspect of obsolescence that really becomes important pretty often. Sarah's probably seen lots of stuff too. I don't know if you want to add anything.
I mean, that's mostly it. There's the mechanical upgrades, but I talked about that a little bit in the last question, so I won't repeat myself there. But really, when we talked about that digital monitoring, FDD, all that kind of off-site stuff and the ability to integrate it, you're dealing with the same limitations that you might be if you had a 10, 15-year-old phone and you're trying to do any of the digital online cloud services. You're just going to run into restrictions there where you do need to upgrade your system. That said, can you improve energy on an older system? Yes, but you can do a lot more if you upgrade your system, and there are ways to upgrade the controls and the network and the system in a way that you're not ripping all the ductwork out.
All right. Another question we have is, can Siemens solutions integrate with existing BMS and laboratory equipment?
So, Siemens is going to be BACnet compatible. We're going to be able to roll up. Obviously, we're going to be compatible with a Siemens building, but because it is BACnet, a lot of times we have when we look at other people doing laboratory controls and stuff like that, there are a lot of companies that are specific as a laboratory control company, and they're rolling up to possibly a different building automation system that's covering the rest of the building. So Siemens is going to be able to operate just like that if there is an existing system in place. We're going to be able to upgrade laboratory controls and roll up to whomever is BACnet compatible and is the main building automation. We can also obviously work within our own system. And then when it comes to building X and the dashboarding, a lot of that is if we can get the data, we can figure out how to make it work. It's just a matter of how accessible the data is in the existing system. Obviously, we've built it to work really easily with Siemens system because it's all compatible in that way, but that doesn't mean we can't pull stuff in that's BACnet from any other type of system as well.
Okay. For hood flow reduction, why not consider converting traditional fume hoods to high performance fume hoods that can reduce flow by up to 40% for both CAV and VAV fume hoods?
That's a good idea. I wouldn't, he asked why not, I would say, definitely consider that. Fume hoods have gotten better over the years, partly as a result of a good test criteria, a good test protocol. A lot of you are aware that, ASHRAE has a fume hood test protocol that measures performance in several ways, including tracer gas containment test. That good and consistent test procedure has led people to recognize that they can make their hoods better, and they've been doing it. So today's fume hoods actually pass those tests, pass those containment tests much better than the old ones. There are people recognizing what are the mechanical characteristics of a better hood compared to a worse one, and looking at how do you renovate a hood without having to tear the thing out. Can you get to those critical spots where the geometry of the hood leads to turbulence, it leads to spills, and they can say, let's put a little, let's adjust this particular aspect of the hood, the bottom of the sash, or the curvature of the sill, and that kind of thing. And so there are people making relatively minor mechanical changes to existing hoods that improve containment and allow lower airflow. So he says, why not consider? I would say, no, sorry, you're right. You should consider hood renovations, hood modifications that would enable safe operation at lower flows.
Yeah, I would agree.
Great idea.
The only thing that I think really drives against it is often we're dealing with a capital cost and a customer who might be trying to lower the cost. But if it's possible to replace it with something that's newer and better, by all means, that's newer and better. Let's do it.
Okay, with the monitoring of unknown chemicals, such as in an R&D facility, how do sensors help evaluate the needed flow? It seemed like you mentioned it was able to look for hazardous presence, but would that work with unknown hazards, or is that keyed in for known hazard locations?
I like that question. Go ahead, Sarah. Go ahead.
I was just going to say, this is where it's very important to have that LVMP established and know what types of chemicals and exposures might be existing in the facility. And if you can't sense for it, then you can't sense for it. Now, this is where we generally are going to work very closely to make sure that the hazards are known and not reduce it if we're not able to measure it. So I don't know if you were going to say something.
Go ahead.
Yeah. Nope. Go. Sorry.
I will add that the concept of demand-controlled ventilation, which can include occupancy-oriented changes, but also can include contaminant sensing variations, if you're using contaminant sensing, if you're using either one, you have to stop and think, how well do my sensors actually tell me what's important here? And we talked about your occupancy sensor maybe tell you the people are gone, but maybe that the hazard has continued. That could be, and that's be a case where you're kind of sensing the wrong thing. In terms of contaminant sensing, you have similar issues. Am I sensing the contaminant of concern? There's a good chance that they're using some stuff that we don't have sensors for. There's a real good chance of that. Am I sensing at the level of concern? Are the sensors I have, sensitive enough for what the hazard is? And finally, are we sensing at the point of exposure? Probably the answer to all three of those is no, okay? Probably the answer to all three is no. How does contaminant sensing make sense? If you can still detect that the people are in the lab doing their work. And if you can detect that something's coming off. Maybe the most important chemical is not sensed, but something's coming off and we're picking it up and we're saying, hey, they're doing their stuff in here. Let's adjust the ventilation. That's frequently the line of thought that justifies a contaminant sensing approach. A lot of people haven't looked at that in that depth, and they think we're sensing contaminants, therefore we're keeping people safe. And there's really a few more steps in the thought process before you can really support that idea. I think contaminant sensing is a great idea, and I think it's important that you have that more complete thought process when you want to apply it. So maybe they're using something that we don't have a sensor for. Maybe that means we shouldn't rely on contaminant sensing, or maybe that means we still pay attention to the solvents that are going to be in the air anyway, or whatever else is going to indicate that they're doing the work. It's not as simple as it sounds.
Okay, and we have time for one more question here. Let's see, have any projects received utility incentive payments for reducing energy consumption?
Yes, lots of the ones that I've worked on have received substantial utility rebates, and this tends to be, obviously this is something that is very different state by state. It's very different based on where you are at with your particular utility company. But I've seen projects a lot of them have like a 50% cap, but I've seen projects get close to that 50% cap where half of the project is being paid for in these utility rebates just because the energy reduction is so great. If you have a hot water system, you do
Did we lose the sound?
I think so. Jim, do you
Yeah,
want to
she's
finish
still
up
talking,
her?
I think, on the
Yeah.
camera.
Do you want to finish up the question there or the answer?
Sarah knows way more about utility rebates than I do. I think the short answer is yes, it's a very common practice.
Okay.
And I see one more question saying, hey, can we do monitoring and remote applications on systems that have other people's control equipment in there? Absolutely, especially if you have some Siemens front end like they mentioned. So yes, it is absolutely possible. The new remote applications are being designed to be independent of where the data came from.
Awesome.
Though you still
Okay.
need a good data
Yep.
connection, like I talked about. If you want to get into data applications, you need a good network.
Okay, and that is all the time we have for today. So thank you for joining us. Feel free to use the QR code, scan that, and take our survey. We really appreciate your feedback. And then a recording of this webinar will be sent to you via email within 24 hours. And feel free to contact the presenters for any questions. Thank you so much for attending, and we hope that you have a great rest of your day. Take care.